Hello everyone, welcome back. This is Mr. Cobalt, and in this video we're going to be going over an introduction to nuclear chemistry. So we're just going to go over the basics. This is going to be a short video. I'm not going to go too deeply into this. So let's get started. But before we do, remember to like this video if you like it. Subscribe to that channel, my channel, and hit that notification bell up on top and put comments in the comment section if you have any questions or would like to share anything with me. Okay, let's get into this. So, nuclear chemistry. So, first thing, we need to talk about subatomic particles. Atoms are made of subatomic particles, meaning that there are smaller particles that make up the atom. So the atom, used a long time ago by John Dalton, used to be thought of as an indivisible particle like a bowling ball or a cannonball or something like that. But now we know that there are smaller particles that the atom is composed of. So those particles are the protons, and the protons are positively charged. So a way that I remember protons are positive is because of P and P. So protons begins with a P, positive begins with a P. So protons are positively charged, and neutrons are neutral, right? So that makes sense. They don't have a charge. So something that is neutral has no charge. So neutrons are neutral. And both of these particles are in the nucleus. So for this video and other videos that I'll be covering on nuclear chemistry are going to focus on these particles in the nucleus, the protons and the neutrons. And then, of course, we have the electrons, which are negative in charge. So electricity, negative charge. So those are on the outside of the atom. They're not in the nucleus. So for nuclear chemistry, we're really not going to be focused on those. So again, our focus is going to be on the nucleus, which is where nuclear chemistry occurs. So this is the part where nuclear chemistry happens. So neutrons and protons is going to be our focus. So what are some examples of nuclear reactions or nuclear activity, right? One example, something called nuclear fission. So nuclear fission is where you split the atom into smaller parts or atoms. So there are examples of where nuclear fission occurs. We can use nuclear fission or radioactive decay to talk about, carbon-14 dating. Carbon-14 is an isotope of carbon. Most carbon that naturally occurs is carbon-12. It has a mass of 12, meaning it has 6 protons, 6 neutrons. But here, carbon-14 is heavier because it has 2 extra neutrons in the nucleus, making it heavier and therefore unstable. And the instability of the nucleus of the carbon-14 atom is what makes it decay. And because of this decaying, we can use it to date living organisms or at least substances that are made up of organic material, things that used to be living. The nuclear bomb is also an example of fission. The power, the energy that comes from the nuclear bomb actually comes from the splitting of many atoms, and that occurs in the explosion. So nuclear bombs give off a huge amount of energy because of the many atoms that are being split. Nuclear power. So we have power plants. So nuclear power uses nuclear fission, the splitting of the atom, to release that power and then harness it to create electricity. And then we have nuclear medicine. So nuclear medicine, those would be things like, using radioactive elements as tracers to help you to figure out whether or not, for example, your thyroid, right? They might use an iodine isotope that's radioactive to investigate your iodine or your thyroid, or they might use a tracer to inject in your body, so that way you can undergo some sort of X-ray or MNR or something like that uh, at the hospital. Other things like um, fighting cancer. So you have chemo. So chemotherapy uses radioactive isotopes to attack cancer cells and kill them. Radon testing in basements. So radon is a radioactive element. Usually, it's in the ground. So if you have a basement, you should usually you check for radon. I don't. It depends on where you live and what's in the ground, but usually you want to do radon testing. And then of course you have chain reactions. So this is an example here as a chain reaction where you split one atom. So you have uranium-235 and it's unstable, so it'll split into two smaller atoms. So this is an example of fission. And then when it splits into smaller atoms, it releases 3 neutrons. Well, these 3 neutrons will then bombard and absorb into other surrounding uranium-235. That's going to make them unstable, and then they split, and so on. So you get what is called a chain reaction. So notice that the first one releases 3, and then these two will break down, and each of those release 3 neutrons. So that's 6 neutrons. So you could see how this chain reaction um, can cascade into a much larger event, and the number of atoms that are splitting exponentially increases. So remember what we said, that more atoms, when an atom splits, energy is released. So if the number of atoms splitting exponentially grows, then that could lead to a very, very large amount of energy being released in a very short time. All right, so what's holding the nucleus together, right? So you might have been thinking about this. If we know that there are protons in the nucleus and the neutrons are neutral, so there's no charge there, and the protons are positive, well, don't positive charges repel each other? That's what we're taught all the time, right? So you bring two positive sides of a magnet together, they're going to want to repel, they're not going to stick together. They're going to push each other away. So same thing with positive charges. So if we've got all these protons in a nucleus and they're all positively charged, why isn't the nucleus just falling apart? Why don't atoms just fall apart and the whole universe and the material world just kind of repel each other and fall apart into particles? So that's the question. Why doesn't the nucleus fall apart? So the reason is because of this thing called a strong force. And the strong force is a special force that acts over like really, really tiny distances. And so in the nucleus, there is a strong force that's holding the nucleus together. So it's kind of like this rope, right? So you got this spring, and the spring wants to unravel. The spring wants to come up, wants to stretch out. It's pulling apart to go back to its normal size, right? But the rope is tied around the spring, kind of holding it together. So the rope is analogous to a strong force. So that there's a strong force holding the nucleus, holding the positive protons together. And part of that strong force it comes from the neutrons that are in the nucleus. So adding neutrons, having neutrons in the nucleus adds to that strong force. But having too many neutrons can be also destabilizing as well. So you don't want too many neutrons as well, because then that'll make it more unstable. So where do radioactive particles and energy come from? So we're talking about how in fission the atoms split apart into smaller atoms, and you get this energy and you get particles also that come from the atom when it splits. So where do these particles come from? So sometimes there are, like as I said, too many neutrons in the nucleus. And so having a nucleus that's really big and having a lot of neutrons in there will actually make the atom or the nucleus unstable. And in order to gain stability, the nucleus will fall apart or will release particles in order to gain more stability. It will release energy in particles. So the atoms will fly apart, break up into smaller atoms. It'll release particles and it'll release energy from the nucleus. So there are three basic kinds of radiation that we're going to talk about. There's other kinds of radiation, but we're not going to talk about those. But we're going to focus on these three basic ones. So radiation comes from the nucleus of an atom. So we talked about how the atom could be unstable because it's too large. There's too many neutrons, maybe too many protons, not enough neutrons to hold it together. So there's a combination of issues here. And so that whatever is making this unstable, an unstable nucleus is going to emit or spit out a particle or energy in order to become more stable. And so the three kinds of particles that could be emitted is an alpha particle, which is given this symbol, the Greek symbol alpha, the first symbol in the Greek alphabet, alpha. And then that's going to be a helium nucleus with a 2+ charge. And so basically you could see that there are 2 protons and 2 neutrons in this nucleus. So this is your alpha particle. This is a helium nucleus without the electrons, right? And so the next particle that could be released is called a beta particle, and that's given the symbol beta, which is the second Greek symbol of the Greek alphabet. And this is like an electron. It's basically an electron. It's the size of the electron, it has a negative charge. It's basically an electron that's coming from the nucleus. So think about that. We're talking about electrons being outside of the nucleus traveling around, but you can get electrons from the nucleus. And this is basically from the breakdown of a proton. A breakdown of a neutron into an electron and a proton. So when you go through beta decay, basically you gain a proton, you lose a neutron, and you gain a proton, and it releases this electron-like particle, and we call that the beta particle. And then the third one is the gamma particle, or we also call it gamma rays. It has no mass. We call it a photon because it's a particle of energy. It's not like a physical particle. It doesn't have mass. It doesn't have charge. So it's a photon. A photon is a particle of energy or particle of light, if you will. So it's very high energy wave or a particle with zero charge. So these are the three basic particles that are released, and the kind of radiation is named after the particle. So if something undergoes alpha decay, that means it's releasing an alpha particle. If it's undergoing beta decay, that means it's releasing a beta particle. And if it's undergoing gamma radiation, then it's releasing a gamma particle or gamma ray. Okay. So what are the charges of these nuclear particles? Well, we just talked about that. Well, how do they determine the charge of these particles? Well, if you have your radioactive substance here, maybe this is an alpha particle emitter, maybe it's a beta particle emitter, maybe it's a gamma ray emitter, right? So basically you have the rays, they go through a slit, so you can get a ray coming through here rather than like a gunshot spread. So you have a split, it goes through the split, and so you get this one ray coming through, and then you got these electrically charged plates that act kind of like magnets, right? So here you have negatively charged, here you have positively charged. So if it's a negatively charged particle, then where's it going to go? Where's it going to be drawn to? Well, negative repels negative, like charges repel, opposites attract. So if this was a negative beta particle, then you would expect it to bend towards the positive plate as it's going through. If it was a positive alpha particle, remember the alpha particle is a neutral, it's a helium nucleus, so it has two protons in there, which make it a 2 plus charge. And so when it goes through, it's going to bend towards the negative plate. If it's a neutral particle, like has no charge, then it's just going to go through undeflected. So beta particles are negative, so they're going to be bending towards the negatively charged plate, or the positively charged plate. And then you have the gamma rays. They have no charge, so they're just going to go right through undeflected. And then, of course, you have your positive alpha particles. So your alpha particles are going to deflect towards the negative plate here. All right, so what about the penetrating power of radiation? So each of these particles have a certain amount of penetration power to them. What do I mean by that? Well, they can penetrate into other substances to a certain extent, right? So some of these particles can go into substances or barrel through substances much farther than others, right? So the question is, can my skin protect me from radiation? What about my clothing? Or will the radiation go through my clothing? Will it go through my body? Things like that. So what's the penetrating power of these sources? Well, here you can see that if you have an alpha source and it's emitting alpha particles are so huge compared to the other two that the atoms and substance in a thick piece of paper is enough to block and keep it from going through. So this large particle runs into other particles pretty easily and so gets stopped by the thick paper. So this is the penetration power of alpha particles is not very large. So your skin can protect you from alpha particles as well as your clothing. So not a lot of penetrating power from alpha particles. Now beta particles, they're like small negative electrons, right? So because they're so small, they can more easily pass through the atoms of your substance here, because remember, atoms are mostly small space. The electrons are very, very, very tiny compared to protons and neutrons. So they can penetrate further into the substance. So a piece of paper is not really going to block a beta particle. So what you'll need is some aluminum foil. So maybe maybe a millimeter or so of aluminum foil will block your beta particle. And what about your gamma ray? Your gamma ray has no mass whatsoever. So because it has no mass, it has a very large penetration power. And so this can barrel through paper pretty easily, aluminum foil pretty easily. You're going to need some thick lead or concrete to block the gamma rays that come from gamma radiation. So that's why a lot of nuclear bunkers and things like that, in case of a nuclear war, nuclear holocaust or whatever, they're usually lined with heavy concrete or lead to block out the gamma radiation. So here's again a picture of what I was just talking about. So alpha particles can be blocked by paper or maybe cornified layer of your skin, so they can be blocked pretty easily. Your beta particle can go through paper, but then a piece of wood about 100 millimeters thick can block your beta particle. And for gamma rays can be go through your paper, your wood, but it can be blocked by about 500 millimeters of concrete, or 50 centimeters of concrete, if you want to think of it that way. And here is a table that you can copy down with all of this information. So you got the three parts of your three particles, right? So three types of radiation. You got your alpha particle from alpha decay or alpha radiation. You got beta particle from beta decay, and you got your gamma rays from your gamma radiation. So what is it made up of? Alpha particles are two protons, two neutrons, basically a helium nucleus. And the symbols for the alpha particle can be either the symbol of helium, because this is a helium nucleus. So you can write the isotope symbol for helium with a mass number of 4 on top and an atomic number of 2 on the bottom, because it has two protons, and the atomic number is the number of protons. The other way you can symbolize it is, instead of having He for helium, you can have the alpha symbol for the first letter of the Greek alphabet, alpha. So you can have this as well. And it has a 2 plus charge because of the two protons, and it can be stopped by paper. Beta particle, as we said, is like an electron, and there are two symbols that you can put for that one. So you have the beta particle, the beta symbol, the second letter of the Greek alphabet, and it's got 0 on top because it has no mass, so the mass number is 0, and it has a negative charge, so you put that on the bottom. So that's one way. You could also symbolize it with E with a negative for electron, because this is pretty much a negative electron, so you could use this symbol. So the charge is negative, and it can be blocked by, as we said, aluminum foil or wood, or even your clothing can block beta particles. Now, gamma rays, those are high speed, high energy waves, light waves. So the two symbols is either this symbol here looks like a ribbon. That's the Greek symbol for gamma, right? Gamma, the third letter in the alphabet. So you can symbolize it with just this symbol here, or you could symbolize it with the zeros, 0 on top for 0 mass and 0 on the bottom for 0 charge. And so again, a thick lead or concrete is going to stop the gamma ray. Okay, I hope this was helpful. I hope you enjoyed this video, and if you learned a lot from it, please make sure you like this video, hit that like button, smash it. Also, subscribe to my channel, hit that notification bell at the top right corner, so that way you can be notified by other videos I put out. Please put a comment in the comment section. Let me know what you think, and if you've got any questions. Thanks for joining me, and have a great day.